So let's talk about a few different ways you can add hydrogen back to a triple bond. The most boring, brute force one is platinum hydrogen. So this is your hydrogenation reaction, and it's much more of a sledgehammer approach. The reason I say it's a sledgehammer approach is we can't stop it. So if we have PTH2, we add something like 2-butene here, we're going to end up recovering butane. So we can't stop this hydrogenation. It completely removes the triple bonds. And sometimes this is a desirable thing to do. But let's say we only want to add one equivalent of hydrogen. Well, we actually have a couple of options here. And these couple of options are going to give us the stereospecificity we want. First option is what's called the Lindlar catalyst. And you'll see lots of different ways of writing this. Sometimes it's PDC, sometimes it's PDCO3, sometimes it's PD plus sodium carbonate or calcium carbonate, sodium carbonate. The point here is that we've taken palladium and we've poisoned it with a layer of carbide carbonate. And what this does is that it makes it makes it hard for it to hydrogenate. The only thing it can really hydrogenate is acetylene or triple bond, an alkyne, and create an alkene out of it. Now, to do this, what has to happen is that the alkyne has to lay down on the surface of the catalyst and the hydrogens come from underneath. So when we do the Lindlar catalyst, we actually end up selecting for a cis alkene when we finish. So the hydrogens are actually added to the same side because of how the catalyst works. So this is a good way to get a cis product across a double bond. But let's say you want to do the trans product. Well, there is a way to do it. And it's sodium metal with ammonia. Now, I talked about in a previous video how we can mix the two of these together, get NaNH2, and this is a good reagent for taking alkenes and producing alkynes. It's also a very good way to take double halogenated alkanes and produce the alkynes. So in that video, I really emphasized how the sodium metal can't be present. Why is that? So I'm gonna have to erase these mechanisms up above. What's happening here is that sodium is actually attacking the alkyne first. Sodium is very good at getting rid of its electrons. If we want to do something even more effective, we could do something like potassium rubidium, but sodium is pretty cheap and readily available. So what will happen is that sodium will give an electron to the alkyne, and this will result in a radical. Now, there's two radicals we can form. We can either form the cis or the trans. In this case, we're actually going to form the trans. And the reason we're going to form the trans is that it's more sterically favorable. If we have the cis, we're going to have two R groups that are in close proximity to each other, but if they're trans, they're opposed. So we don't get any of the cis product out of this. This alkyne, or alkene, is very good at removing hydrogens from ammonia. And so what we'll end up doing on both sides of this is forming this compound. So if we want to add hydrogen in a trans position, what we'll do is we'll do sodium metal and NH3. Now again, we are going to produce some of this NaNH2. If we don't have halogens, meaning that there are no halogens added across this double bond, which we shouldn't have if we're starting with the alkyne anyway, we don't have to worry about converting back and forth between the alkene and the alkyne. But these are the three ways you can practically add hydrogen to a triple bond. You can do the PTH2, platinum hydrogen, completely eliminate the triple bond, give you back to an alkane. If you only want to go back to an alkene, but you want it to be a cis when you finish, do the Lindlar catalyst, the PDC plus hydrogen. And if you want to go to the alkene, but you want to be a trans configuration, the NaNH3 will get you there.